Today we're going to have a closer look at metal mobility and ligands, and in particular, a closer look at gold. What we're talking about here is the story of how metals move. And in this, have you ever wondered how metals move from point A to point B? Notwithstanding processes such as colloidal gold, metals move via complexation with ligands. And to keep this talk exciting, we're going to talk about gold in high sulfidation epithermal environments as we walk through the importance of understanding the properties of the metals you're exploring for and the environment that you're exploring in order to better understand how to think about your system. So first, what's a ligand? A ligand is an ion or a molecule attached to a metal ion by coordinate bonding. The bonding with the metal generally involves formal donation of one or more of the ligand's electron pairs. And the nature of metal ligand bonding can range from covalent to ionic, so general things that we learned in chemistry back in the day. In general, ligands are viewed as electron donors and the metals are electron acceptors. So in other words, Lewis bases and Lewis acids. And finally, ligands in metals can be ordered in many ways. One ranking system focuses on ligand hardness. And to your right, you'll see an example of a cobalt-3 complex that contains 3 ammonia ligands, which are monodentate. And in this example, the chloride is not a ligand. Now, I don't want to make any enemies out of anyone here, but considering that you're already watching this video, I want to clarify that this slide here is adjusting the real IP, as distinct from the black magic kind, in other words, geophysics. We're talking about geochemistry and ionic potential. Ionic potential is simply an element's charge divided by its radius. And why is this important? It's because it gives a sense of how strongly or weakly the ion will be electrostatically attracted to ions of opposite charge and to what extent the ion will repel other ions of like charge, which has implications on how cations behave in solution. Following this, there's an appreciable number of ligands or anions that potentially can facilitate metal or cation transport in hydrothermal fluids by forming metal complexes. The important question here for economic geologists is which of these ligands can form stable complexes with the metals of interest and can thus play a role in their transport. For a predictive tool to aid in trying to answer this question, we can turn to Pearson, who subdivided metals and their ligands into 2 groups, namely small and strongly charged ions, which he termed hard acids and bases, and large, weakly charged, and easy polarizable ions, which he termed soft acids and bases. You can see all of this in the table to the right. He proposed that in a case of competition among ions, hard acids or metals will bond preferentially with hard bases, the ligands, and do so ionically, or by transferring electrons, whereas soft acids will bond preferentially with soft bases, the ligands, and do so covalently, or by sharing electrons. He also recognized an intermediate group of ions which can bond with either hard or soft ions, and he called these borderline. Despite the difficulty in quantifying this principle, if used qualitatively, it provides a really good starting point for predicting the likely behavior of metals in the presence of different ligands, and in general, its predictions of the relative stability in metal complexes have been born out of the available experimental data in hydrothermal solutions. Continuing down this path, gold is typically found in nature as gold +1, and it's considered a soft metal and will tend to bond with soft ligands. We're not going to focus so much more on gold in the 3+ state, but this harder form is important because only under really oxidizing conditions at ambient temperature. An additional characteristic of gold which relates to its softness is that the outer electron cloud is readily delocalized, which allows for electron transfer and weak bonding between gold atoms, which leads to the formation of clusters which charge surfaces, mainly negative, that repel each other and in turn form colloids. If you guys have ever heard of colloidal transport, this is the mechanism by which this is happening. So the speciation of gold in hydrothermal systems is relatively simple. The most important ligand at temperatures in the high sulfidation environment is HS negative, with AuHS2 negative at higher pH and AuHS0 at lower pH. I've also included here some information about it in porphyry systems, but we're not going to really get into that here. At the right is a really cool diagram that was put out there by King et al. In 2014, which just has a look at how gold will be traveling from in the epithermal environment from the magmatic system up through the hydrothermal system, and how eventually one of the mechanisms by which it is absorbed onto the growing surfaces of pyrite for deposition. Now that we've gone over some chemistry basics, I want to introduce a diagram that's very helpful when talking about the transport of gold as a chloride and as a bisulfide species. Quick parameters that we have are gold solubility and ppb and molality, which you have on both of the y-axes, and speciation. The different complexes are seen in the different colors. At 1 kilobar pressure and as a function of temperature in degrees Celsius, which you can see on the x-axis, for an aqueous solution containing 1.5 NaCl and a 0.5 MkCl solution. The difference between the top and the bottom graph are the conditions of the experiments, a difference in total sulfur, and in turn what mineral assemblage the oxygen fugacity is buffered by. Now, look at the black dashed lines. This is the total solubility of gold in solution. The colored lines are different gold complexes. Au bisulfide complexes are by far the most effective in these systems at lower temperatures, such as in these epithermal environments, whereas chloride complexes dominate at higher temperatures, for example, in the porphyry domain. In other words, what seems to be a complicated diagram now is pretty easy to understand. There's so much still to get through that I don't want to spend a ton of time talking about this, but to our right, you have a diagram of idealized high sulfidation epithermal system. And the text gives two reactions by gold is governed in these systems, both in transport and its deposition. The deposition of gold is promoted by a decrease in the activity of HS- and oxygen fugacity, as well as an increase in pH. So speaking of my last point, this diagram explains the transport and deposition of gold in these systems very well. Breaking down the graph, the dashed lines denote regions of predominance of ligand availability for transporting gold, temperature, pressure, activity, etc. These are predetermined in this diagram, but otherwise these are a function of oxygen fugacity and pH. Gold solubility is in the solid black lines, and where it starts getting yellow and red, those are the optimal conditions for gold solubility in this system. So how do we interpret this glorious graph? Let's look at the solubility of gold as a species AuHS2-. Its concentration reaches a maximum at FO2 pH conditions here. A small increase in FO2 leads to a precipitous drop in HS- concentration and consequently gold solubility. And as a result, deposition of gold at these conditions is strongly favored by oxidation and could occur through the interaction, for example, of the ore-bearing fluid with an oxidized host rock or mixing with oxygenated meteoric waters. So taking in all that we've learned in the first 7 slides, we're going to look at 2 mechanisms for hydrothermal transport and deposition of gold in the epithermal environment. The first is the vapor transport of gold. The vapor condenses some hypersaline liquid at deeper levels where it's forming porphyry deposits. And then at subvolcanic levels in the high sulfidation epithermal environment, the remaining vapor either condenses to form an acidic liquid from which these deposits directly form, or the deposit can form the vapor that contracts to a liquid without condensation. And here, this is an example of work being done at the Cowiigan volcano, which is an actively forming high sulfidation system. Another process for gold transport in these systems can be through the colloidal transport of gold. Here, if gold-bearing solutions become supersaturated due to, for example, a sharp drop in temperature, instead of precipitating the gold, they may nucleate negatively charged colloidal particles that repel each other, allowing the gold to remain indefinitely in suspension and be available for further transport. The deposition of gold will occur as a result of flocculation due to changes in the fluid chemistry, such as an increase of salinity or pH, both of which may occur as a result of boiling or fluid mixing. However, colloidal gold may also be absorbed onto minerals with positive surface charges, for example, p-type conductors, such as arsenide pyrite, a hypothesis that may explain the invisible gold in some deposits. How do I apply this information? In your own projects, it's important to understand that the metals of interest and the environment that you are working in. So for example, what type of deposit are you looking for? What is a favorable host rock, fluid pathway? How are the metals of interest deposited? And thinking in terms of geochemistry can be very helpful, as many times ore deposits will form due to redox, pressure, or temperature changes. Keep in mind that fundamental understanding of other variables in your system, for example, structure, geology, etc., these are all equally important.